Hello? Hello?
Just be there.
Oh, okay. Okay, hello to all. My name is Abul Fazl. I'm a second-year PhD student under the supervision of Manuel Soler. And today I'm going to speak about my research progress, which is about thesis, robust aircraft trajectory optimization for the benefit of climate. I'm going to start with the motivation. As we all know, aviation is contributing to global warming through the emission of CO2 and other non-CO2 effects, and due to the strong growth rate of aviation, the expected critical increase in climate impact is expected. Reduction of climate impact associated with CO2 emission relies on technical aspects such as improving aircraft efficiency, novel propulsion, but for non-CO2, which is responsible for approximately 2/3 of aviation radiative forcing, can be mitigated with planning aircraft trajectories to avoid climate-sensitive regions. Because non-CO2 climate impact highly depends on location, time, and altitude of the emission. Numerous studies have been proposed in literature to find climate-optimal trajectories or climate-aware trajectories, but these methods differ in how they identify these climate hotspots, the orange polygons, and how they include the information to plan climate-aware trajectory with which optimization methods. In this respect, we have conducted a survey and strategies and proposed some classification of objective function considered in the cost function of the optimization problem, and also trajectory optimization solvers. After reviewing all these works, we found 4 scientific gaps main, and which is about uncertainty, efficient trajectory optimization solvers, network climate optimal trajectories, and new models for hydrogen aircraft. The first two, the consideration of uncertainty and efficient trajectory optimization, will be addressed in my thesis. Uncertainty, as mentioned, the mitigation of climate impact associated with non-CO2 emission can be obtained by avoiding climate-sensitive regions. If these climate-sensitive regions, the determination of them affects by uncertainty, mainly due to climate science, meteorological forecast, and emission calculation. So, if these sources of uncertainty not considered in planning aircraft trajectory, it will result in unreliable and inefficient trajectories. And also, after identify sources of uncertainty and quantify the impact, the optimization method should be capable of considering this uncertainty to plan robust aircraft trajectory in computationally fast manner, comparable with operations. Also, we found another interesting topic to be addressed, the quantification cost of climate impact, which can result in economically beneficial trajectories. So these 3 parts will be addressed in my thesis and objective. To do so, we need first quantify the climate impact, then quantify the sources of uncertainty. Before going to problem formulation, I want to speak about the quantification of climate impact. We basically make use of algorithmic climate change functions developed within European project ATM4E, and now is currently under modification within Fly ATM4E project, the project that we participate in. And these functions take atmospheric variables and input and quantify the climate impact of each species, CO2, non-CO2, for example, NOx, water vapor, in terms of average temperature response over the next 20 years. For this purpose, we developed a library as a part of our contribution to ALARM and Fly ATM4E projects. Here you can see some information about the library. Hopefully, it will be released soon, before summer break. This is the structure of the library. It takes forecast data as input, and with respect to some user-defined configuration, provides estimation of climate impact for each individual SCCFs, and the merge one, combining the effects of all, and climate hotspot, those areas that are highly sensitive to aircraft emission. After quantification of climate impact, we need to quantify the sources of uncertainty for robust trajectory planning. At the first step, we consider only uncertainty in meteorological weather variables. Why we do? Why is the reason? Because meteorological uncertainties such as wind and temperature uncertainty in those variables will directly affect the aircraft trajectories. And also, ACCFs presented in previous slide require some meteorological variables. So they are also affected by uncertainty. To have a quantification of uncertainty in meteorological weather data obtained from forecasts, we make use of ensemble prediction system, which provides normally n different forecasts. And now we can state the optimization problem. Of course, there are different elements that exist in formulating problem formulation, such as aircraft dynamical model, which we use point path model and different path and boundary constraints. But now I'm just presenting the considered cost functional of the optimization. As can be seen, it is weighted sum of simple operating cost, which is a function of flight time and fuel burn linearly, and average temperature response, which presents the climate impact obtained by considering ACCFs. There are two parameters here, CI and EI, that base these two objectives, and we do this selection to just work with alpha. And so if CI equals 0, it is climate optimal, it only considers this part. If alpha is 1, it only considers cost. We propose two approaches for finding robust climate optimal trajectory. The first one is for structural space. This is a heuristic graph-based algorithm that parallel on GPU. It is very fast, and I'm not going into mathematical details, but this is the scenario. I'm going to show the results. Different sources of uncertainty considered: initial flight time, initial flight mass, and weather variables. 10 assembled members have been considered, and this is the results. As mentioned, alpha varies between 0 and 1. Alpha 1 is cost optimal, the blue line here, and alpha 0 is climate optimal, the yellow one. This is the obtained vertical profile, flight level. We can see that for the climate optimal one, it tries to fly at altitude that no formation of persistent contrails is. And for cost optimal one, it flies through contrails. If you look at the obtained climate impact, we can see that the yellow one results in lower climate impact, and the optimization is also very fast, 3 seconds for this problem. And also another interesting result that can be seen here. This is the lateral path depicted with the speed of wind. You can see that the cost optimal one, the blue one, is not necessarily the shortest path because of the effects of meteorological condition. Here is wind. We want to use stronger tailwinds. This is the results for different alphas, the Pareto frontiers. This is their absolute values with ranges of uncertainty. As mentioned, these uncertainties are due to the consideration of ensemble weather forecast. And we can see that by decreasing alpha, not only the dispersion, not only the mean value, but the dispersion of climate impact also decreases. And this is the absolute values reported based on mean values. 60% of climate impact can be reduced by 4.4% increase in cost, and the mitigation potential mainly achieved by avoiding contrails, because it has sharp behavior and very efficient in trajectory planning to be avoided. And also the average temperature response of country has the largest climate impact. We also apply this methodology to the scenario that defined between flight TM4E, the optimization of top 100 route ranked using available seat kilometers for 2 different months and 5 representative days within this month, December and June, and we can see that the mitigation potential obtained are different, are not necessarily the same because the change of atmospheric condition. For example, for 5th of June, it is possible to have more than 50% decrease in climate impact, but for 15th of December, it's not possible to have more than 20% decrease in climate impact. Now I'm going to present the second approach. This is robot. Okay. This is based on robust optimal control. This is for fuel root aerospace. And the idea behind this approach is to expand the dynamical model of aircraft, considering the scenarios, different scenarios obtained from considering ensemble weather forecast, and then convert the optimization to the deterministic one, which is solved with direct optimal control with the setting mentioned here. This is also a scenario. This is two-dimensional only lateral path optimization. And the objective function is as the same we considered before. Again, we work with alpha. We can see that as we decrease alpha, the aircraft tends to avoid climate-sensitive regions. And here are the obtained Pareto frontiers. This is the relative one, and this is the absolute one with ranges of uncertainty. Again, here, by decreasing, not only mean value decreases, but also the dispersion, because we avoid highly uncertain regions. Okay. Now, according to the result presented, the mitigation potential of climate impact can only be achieved by increasing in cost. For example, because aircraft tends to fly longer routes, because they want to avoid climate-sensitive regions. This is not favorable for airliners because of such increase in cost. So there is a need for climate policy, because in the current market-based instrument, there is not any climate policy for non-CO2 climate effects, mainly due to the uncertainty in understanding the climate impact. But we have for CO2, for example, we have taxes for CO2 emission and this kind of thing. We propose two approaches to quantify the cost of climate impact. Then we motivate airliners to adopt climate optimized trajectory, finding those trajectories that are also economically beneficial. The first one is, the idea is based on equivalent CO2 emission. We scale the climate impact of non-CO2 emission based on CO2, and then apply the tax of CO2 for non-CO2 climate impact. The other one is the concept of climate charge airspace. We consider charge for emitting in areas that are highly sensitive to climate impact. I'm going to show results based on approach 2, concept of climate charge airspace. We penalize or we assign charges to areas that are highly sensitive to aircraft emission. And here, this is the simple operating cost that previously mentioned. It considers only flight time and fuel burn, but now we include the cost of emitting in climate-sensitive regions with parameter climate charge. Now we want to see how the shape of Pareto frontier changes. This is the scenario previously considered, for free route airspace. This is the one obtained in before, free of charge, because the climate charge is 0. But as we increase the climate charge, the shape of Pareto frontiers changes. Now we can see that previously called a climate optimal, cost optimal trajectory is not necessarily the cost optimal one, but and there is a potential to find win-win situations. For example, here this is the win-win situation instead of this, and this situation changes with different charges. Okay, now I'm going to present some outcomes. These are the outcomes of my research. The first part is related to directly related to my thesis, which will be included in my thesis, but the rest are obtained with collaboration with my colleagues, but all of them are related to climate optimal trajectory planning. And as for next step, I'm going on research essay hopefully from mid of December, and the main objective of my research essay is to sync our trajectory optimization tool with their climate models. And as mentioned, the approach proposed for free route airspace is 2-dimensional. We want to extend the result to 4-dimensional. Also explore different approaches to quantify the cost of climate impact, because this was the method I presented was just a preliminary studies, and efficient, robust, Pareto optimal solution. This is mainly for calculating aggregated result, not individual one. Aggregate, find an optimal behavior of a set of trajectory, not only one. And also develop learning-based approaches to, mainly based on approximate learning programming, to find climate optimal trajectory in robust manner. And also identify different sources of uncertainty, such as emission calculation, because they are uncertain, and address them in planning climate-aware trajectories. Thank you.